Ladies and gents, we're going to do a quick autopsy on this old PC power supply. This is an old ATX power supply. It's a hyper 525 watt power supply from an old PC. The PC is an old AMD Athlon XP, remember those? And I think this was a replacement power supply because the original one packed up. But this one is old, and while it still works, it's not very good, and the computer doesn't actually work very well. I've had to down clock the PC from 1.5 gigahertz to 1 gigahertz because it just keeps crashing. And the motherboard had failed with lots of dud capacitors, but actually this power supply is still suffering from lots of bad capacitors. So these capacitors here, these are the main output filter capacitors. They've got domed tops, and if we look down here you can actually see some of them have actually leaked. You can see the sort of chemical debris leaking on the top, and these are complete junk capacitors. There's no manufacturer name anywhere near these. So what we're going to do is we're just going to take a quick look at this, and we're going to look and see how they work. So let's start with the power input here. So we've got our fairly standard IEC power input connector here. Beneath that is a fan control switch. We'll ignore that. So this is a fairly standard OEM module consisting of the connector here and a pre-made EMI filter, and this comprises a common mode inductor here and a polypropylene X2 grade capacitor. Fairly straightforward, nothing clever there. Now the next stage in this is the mains input comes to this area here, which is the surge control area. So we've got these things here which are capacitors, and these things here which are metal oxide varistors or surge protectors. There's also a fuse in here, which is interestingly soldered into place, and there is an opaque heat shrink tubing placed over the glass case, so you can't actually see where it's broken, whether it's blown or not. Very interesting, clearly designed so you can't repair this device. And then here we've got some filter. This is the filter choke. Again, this is another, looks like a common mode choke. Capacitor underneath it. Again, probably another polypropylene X2 class, and hiding just underneath it, and it's very, very difficult to actually show you this, there is a bridge rectifier, and there it is. From there, this power supply uses what's called active power factor correction, and we'll talk about that a bit later, but it does not go direct to the capacitors. Instead, it goes to this board, and this board here takes the full wave rectified DC from the bridge rectifier, and actually this is a voltage booster. So this is a switched mode voltage booster. We have let me just turn this around so I can show you this. We have a control IC here, a little bit of control electronics. We have here a transistor and a diode and an inductor, and in fact this circuit is identical to a fairly typical flyback transformer, or it's actually, sorry, not a transformer, it's a flyback inductor, as you'd find in, say, a TV or a car ignition system. The difference here is that we don't actually have a second winding on this inductor, and instead we take the high voltage directly from this winding, single winding. So the power is turned on and off with the main transistor, and the high voltage is caught with this diode, and the high voltage then runs off to the reservoir capacitor. So actually this device has the effect of boosting the voltage. And in fact it is a boost regulator, so it actually regulates the voltage at about 380 volts DC. Of course, if you full wave rectify mains voltage of 240 volts, you get 340 volts DC because the capacitors and the diodes catch the peak voltage, which is 340. And also in the case of a power supply such as this, if you apply 120 volt AC and you select the switch to AC 120 volts, the bridge rectifier is reconfigured into a voltage doubling rectifier, so you actually still get 340 volts in these capacitors. In this case, with the power factor correcting boost converter, we get a voltage of about 385 to 390 volts in these capacitors. From there, the next step after the smoothing capacitors is an inverter. And the inverter is relatively simple in this case. This is a very simple 2-transistor inverter. There are 2 transistors underneath this heatsink here. I can't really show you them very clearly, but there are 2 here, and there's a diode on the front here. So inverter, and from the inverter is your transformer. So there's a transformer here which takes the 385 volt AC, and it's got a couple of windings on the back. It's got a 5 volt winding and it's got a 12 volt winding, and there, after the transformer, are 2 big rectifier diodes here. In fact, these are double diodes. So you've got two half-wave rectifiers for 5 volts, 2 half-wave rectifiers for 12 volts, giving from a center-tapped winding here. This little transformer here is actually for the standby power and for the other minor power supplies like -5 and -12 volts, which have very low power demand. So this for standby power is energized all the time by a separate smaller inverter, and the big one is energized when the main power supply is running. And then from here, we've seen the diodes here. Then we've got some more diodes here, and then we've got the smoothing filters. So there are reservoir capacitors and smoothing inductors here. Again, this is probably the 12 volt one, 5 volt one, smoothing capacitors. And there'll also in here be somewhere here probably is a regulator inductor for the 3.3 volt supply. Actually, I may have got this wrong. One of these may in fact be the 3 volt regulator, because the 3 volt supply comes from the 5 volt supply via another step down regulator. Unfortunately, I can't take the thing apart enough to work out which one is which. But these are the smoothing capacitors, and then there is the main output. So how's the voltage regulated? Well, what happens is there are connections here to the main output which run back here on the circuit board, and there are some very interesting little devices down here. There. And these devices are LEDs. There's an LED in here and a photosensor here. And this device here is actually not a transistor, it's a voltage sensor. What it does is it triggers when the voltage reaches the correct voltage, and then it turns on this LED, and then there's a sensor here which tells the inverter, there's an inverter circuit here, whether the voltage is correct. So if the voltage goes up too high, the LED goes on brighter than normal, tells the inverter to reduce power. If the voltage drops, the LED goes out and the inverter increases the power. So that's how the voltage regulation works. So all in all, very densely packed, very densely packed circuit, very difficult, and has clearly been built to the lowest possible cost. These capacitors are complete junk, total junk. I'm also very doubtful that you'd be able to get a full 500 watts through this transformer. It also looks as if it's got a little bit hot. The insulation is starting to go and discolour. And again, I don't think these transistors and diodes are quite rated to the currents that this thing claims to do. And of course, just to add insult to injury, we've got the heat shrinked fuse, just to make things really difficult. Interestingly, the power factor correction board is actually built to slightly better quality, presumably because that's an OEM part that the manufacturer has just bought in rather than designing from scratch. Interesting.
Okay, this is just a schematic I've drawn, very crude, just to show you how a typical ATX power supply will work. So here we have the mains input here. in this case 230 to 240 volts AC. You've got an EMI filter, surge protection, and various other things here. Rectifier, again typical 4-diode bridge rectifier. Now in this case we've got this voltage boosting circuit, and the reason it's there is to correct the power factor. The problem with a standard rectifier and a capacitor combo is that the capacitor takes a big spike of current when the voltage reaches peak and virtually no current elsewhere. This circuit actually modifies the current into the capacitor so that it is proportional to the mains voltage, and so it avoids the problem of big spikes and distortion of the mains voltage waveform. So we then got the big smoothing capacitor here. In this case it's running at about 385 to 390 volts because of the voltage raising effect of the power factor corrector. We've then got the inverter here, which runs at about 20 to 50 kilohertz, and then there's the transformer. Now the transformer is needed to actually convert the voltage by a large margin. It's the most efficient way of doing it, and it is also necessary for safety, so it actually means there's no direct connection between the main supply and the outputs. The reason it's done with an inverter to raise the frequency to about 20 kilohertz to 50 kilohertz is because transformers become much more efficient and much smaller and much cheaper when they're operated at high frequency. So in the US, where they have 60 hertz electricity, the transformers are actually slightly cheaper, slightly smaller and slightly more efficient than in places like Europe, where they have a 50 hertz power supply. And if we take this to the extreme, 20,000 to 50,000 hertz, then you can make the transformers very tiny indeed. So inverter, transformer, then of course we've still got AC, so we need a rectifier, and then finally smoothing capacitors, and there's your output, in this case 5 and 12 volts DC. The trick of the power supply and how it maintains a regulated voltage is that there's a voltage detection circuit, which I pointed out, an LED and a photodiode, which then sends the signal back to the inverter to control its power. And the reason that you have this LED photodiode system is again for safety. If you connected the voltage detection circuit direct to the inverter, you would subvert the safety factor from the isolation of the two windings in the transformer. So you need some sort of barrier, and in this case you have the LED, then a little piece of glass or ceramic, and then the photodiode to make sure there's no electrical connection. So there you go, ATX power supply.